Hi everyone, this is Jason Key at SB Grid in Boston. So thank you for joining us for our webinar today. So today we have James Foadi joining us from Diamond in the UK. He's going to tell us about assembling data from multiple crystals with Blend. So go ahead, James.
Hello, thank you very much, Jason. And thank you very much also to the SB Grid members for being interested in Blend. I'll be very happy to give this webinar today. So I've got these next slides and before the official slide to start.
Yep, looks good.
So this is my first slide. Right, so in the course of the next 30 to 40 minutes, I try to justify why in recent times it has become increasingly common in macromolecular crystallography to create complete data sets using multiple crystals. I will shortly introduce and explain Blend, which is a CCP4 program, and whose aim is to help users to assemble data from multiple crystals, like you said. And I will try to show a bit more in details with a tutorial how the program can be used effectively. So let's start discussing why just one crystal is not enough any longer to solve crystal structures. Of course, this is not really true. A nice, good-sized homogeneous crystal that survives a whole data collection is always going to be the preferred choice for crystallographers. But such crystals are not easy to obtain, especially for difficult structures like membrane proteins or protein complexes. And when the optimization strategy for crystal growth is successful, this normally, as you well know, requires long periods. So these days, it's much more common to grow crystals that are prone to degradation during data collection. Crystal size is also in general an issue. Small size means weak intensities, and at third generation synchrotrons, beam size can be matched to crystal volume, and the beam flux is very high. So moderate reflection intensities can be collected also from small crystals, but of course, crystals will degrade even faster with such intense beams. Therefore, in general, radiation damage means that crystals die before a complete dataset can be collected. And furthermore, data redundancy, which is probably better expressed as reflection multiplicity, can increase the signal-to-noise ratio for anomalous phasing. This has been clearly shown to be the case for multiple crystals, thanks to the work of Hendrickson and collaborators started already 5-6 years ago. And working with multiple crystals leads immediately to two major problems. The first concerns crystal similarity, better known as isomorphism. It is clear that data quality depends on crystals isomorphism. The second major problem is related to the number of possible combinations from groups of crystals. Crystals isomorphism has been known and studied for a number of years. We can see here 4 papers that deals with the problem. The first 2 are historically important works in relation to the isomorphous replacement method, where structural similarity across crystals is essential for success. The third paper investigates the significance of decimals in the determination of unit cell parameters, and also this is closely related to crystal similarity. The fourth paper is interesting and important because it tries to link experimental aspects of crystallization and data collection to unit cell parameter variation. It is tempting and perhaps is also useful to characterize crystal differences via factors broadly divided in 2 main groups, which are connected to the variation of either unit cell parameters or diffraction intensities. In the unit cell parameter group, we could place crystal packing, global structural changes, which means changes that affect the crystal lattice as a whole, the variable solvent content for particular classes of proteins like membrane proteins, and also the strain induced by the process of flash cryocooling. Closely connected to differences in diffraction intensities are structural changes at a local level and the formation of crystal derivatives via diffusion of heavy atoms through crystal channels. In addition to this, unit cell parameters have very little variation when data are collected from crystals at room temperature. for example, in situ directly from crystallization plates. But in reality, factors in one group can easily induce effects on the other group. For example, the diffusion of heavy atoms through solvent channels can induce tiny dislocation of structural motifs that gradually modify the whole crystal lattice. The extent of the problem connected to the combination of crystals in groups can easily be grasped by looking at a numerical example. If we have 10 datasets collected from 10 crystals, we can combine individual datasets and can form 10 groups of 1 crystal each, or 45 groups of 2 crystals each, or 120 groups of 3 crystals each, and so on. In total, we arrive at 1,023 possible combinations. And using the binomial theorem, it is straightforward to calculate that 2 to the power of n minus 1 possible datasets can be assembled out of n crystals. A number that can become very large indeed. It is clear that there are time limitations to create all possible combinations of data from multiple crystals. And among the many solutions to the two problems just described, we have adopted one that makes use of cluster analysis. In hierarchical cluster analysis, n-1 clusters are formed out of n objects. This number is orders of magnitude smaller than the 2 to the power n value mentioned before. Furthermore, clusters are formed out of similar objects. With cluster analysis, we obtain a manageable number of datasets with decreasing isomorphism, matched by increasing completeness and multiplicity. Of course, the final number and quality of datasets will depend very much from the quality and completeness of the individual datasets and from their level of isomorphism. At Diamond, we have implemented cluster analysis in the computer program Blend, which is the product of a collaboration with the Membrane Protein Laboratory, the MPL, and the CCP4. And here you can find the main reference dated 2013. I'm showing here a schematic on how Blend works. The input consists of integrated but unscaled data. And these are MTZ or XDS files, typically produced by integration programs like MOSFilm, XDS, and Dials. Blend can be executed in analysis, synthesis, or combination mode. The analysis mode needs to be executed at least once at the beginning of any session with new data. In this mode, all data are checked for validity. For example, they must include only single sweeps. They are checked for the amount of degradation due to radiation damage and for resolution. Finally, data are combined in clusters using unit cell parameters to measure datasets similarity. The dendrogram illustrating the results from cluster analysis and other files are created in the running directory. At this point, and after having analyzed the results produced, the user can execute Blend in synthesis or combination mode to produce scaled and merged files from datasets assembled as clusters or groups specifically selected. All files which are in MTZ format and the related log files for the pointless and aimless runs are included in either a directory called merged files for the synthesis mode or a directory called combined files for the combination mode. These files can be next used for phasing, model building, refinement with other programs. All processes are regulated and controlled by users via keywords, all having appropriate default values. A new mode has been recently introduced in the program with the aim of guiding the selection and filtering of datasets in combination mode. This is the graphics mode, and at the moment it includes procedures to produce dendrograms with specific annotated values around each cluster node. In future, it will include procedure for the production of additional graphics, like, for instance, the reciprocal spade completeness diagrams. Let's now get down to business, to the actual working of the program with the tutorial. Two sets of crystals from lysozyme have been considered here jointly for educational reasons. The first set comes from in situ room temperature native crystals. The second from cryocool crystals previously soaked in a solution of sodium bromide. Now, the reason why I have chosen this is because unit cell parameters are very close between these two groups, but are also systematically different, so that we have two slightly non-isomorphous sets of crystals. Data for this tutorial can be downloaded from the links I will include at the end of the webinar. Here, they have been all placed in a directory called lysozyme under the subdirectory data. The tutorial will be carried out in a subdirectory called tutorial 01. So let's move to this directory to start our tutorial. The tutorial itself will be here illustrated using command line, but it can be easily repeated via CCP4I. To execute blend in analysis mode, so at the beginning of the process, we simply type blend -a followed by the path to where all data are included, in this case, data lysozyme directory. The program execution starts, showing the version and the main program reference of 2013. Now, in the official blend documentation in the CCP4 website, we have also included references to Pointless and Aimless because Blend makes systematic use of these programs. The users are encouraged to add citations of Pointless and Aimless when they cite Blend. The program automatically halts, waiting for keywords input. Pressing the Enter key signals the program to include default values for all keywords. The program thus restores execution by loading all datasets in the target directory. Files that are not valid are flagged accordingly. And so there are numbers to understand why, if at all, they have been rejected. In this tutorial, for example, all 28 input files are flagged as acceptable for further processing. Next, data are partitioned in groups with same Bravell lattice for display purposes. In fact, cluster analysis will be carried out on all input datasets, irrespective of their initial lattice. Next, cell parameters, volume, mosaicity, nominal resolution, distance to detector, and wavelength are displayed in a summary table. The same table is saved as blendsummary.txt file for later reference. This table is useful for various reasons. In this example, for instance, it is easy to spot datasets 19 and 21 as having values very different from the others. In this case, it should be due to wrong indexing. Next, the procedure to detect overall degradation due to radiation damage is performed. The procedure goes as follows. In this picture, we can see intensities values averaged in resolution shells, each curve including reflections from groups of 3 images at a time. Bluish curves indicate data from initial images during data collection. Reddish curves indicate data from final images. Degradation from radiation damage means that bluish curves should be higher than reddish curves. Besides, this decrease should be faster at higher resolutions. Now, Blend attempts a regression of average intensities versus image number for each resolution bin, using an exponential as linear model. If the slopes of the linear model that describes the rapidity of the degradation increase linearly with resolution, then the specific dataset is flagged as having been severely affected by radiation damage. In this case, an image number is calculated, after which intensities are expected on average to have a decrease of more than 25% of their initial value. This 25% value is a default value and can be changed using the keyword radfrac. This number for each dataset is written to a file called finallistoffiles.dat. As you can see, the file lists all paths to the used datasets with the assigned serial number at column 2. Columns 4 and 5 describe initial and final image numbers, while the cut suggested by the radiation damage procedure is reported at column 3. The last column reports an estimated resolution cut. Data averaged at resolution higher than this cut should have signal-to-noise ratios smaller than 1.5. It is important to remember that empirically, this is a cautious choice and that users can attempt extending resolution beyond the suggested values. In the final part of the execution, cluster analysis is finally performed using cell parameters to measure similarities between datasets. The related dendrogram is written out as a PNG file and as an ASCII file. In Blend, it is also possible to use averaged intensities in resolution shells as measure of similarity. This is controlled by the keyword cparwt. A value equal 1 means use cell parameters. A value equal 0 means use average intensities. But this is not the default, because tests we have done using this option have not given consistently interpretable results. Now, in these slides, we can see the dendrogram on the left and how similarity is measured by the so-called word distance. This distance forms part of the algorithm used to carry out cluster analysis and is not easily reconducible to absolute unit cell differences in angstroms. For this reason, in Blend, an indicator of cell similarity has been introduced to make it easier for users to judge how similar or different unit cells are. It is called absolute linear cell variation, or ALCV in short, and its meaning can be understood by looking at the top right drawing, where two different unit cells are displayed. A diagonal is calculated on each of the three main faces, along with its variation across all crystals analyzed. The largest of these variations in angstrom is the absolute linear cell variation. Its relative counterpart in percentage is called linear cell variation, or LCV. At the bottom of this slide, we can see the ASCII counterpart of the graphical dendrogram. This file, called clusters.txt, has numerical details for all nodes of the dendrogram and is therefore extremely useful. In the specific case under investigation, we can notice that the two datasets 19 and 21 are the last ones to cluster with the rest. They are outlier and could possibly be a byproduct of wrong indexing. As their contribution to the overall calculation is very small, they can be eliminated from the analysis. And this is how we proceed. A file named mtz_names.dat has been automatically created by the previous run of Blend with the list of valid input files. The file can be copied into a new file called, for instance, myinput.dat. And in this file, the lines related to datasets 19 and 21 are deleted. Blend is executed once again in analysis mode, but this time the input, as you can see, is a file rather than a directory. The program still halts, waiting for keywords input, and we can press again Enter to assign default values. Once again, the program executes to the end, but we have to remember that now we are dealing with 26 rather than 28 datasets, and that the dendrogram will have changed slightly. The dendrogram shows very clearly two branches corresponding to the two different groups with which we assembled the original group of data. At this point, we would like to create scaled and merged data for some of the nodes of the dendrogram by executing Blend in synthesis mode. This can be done by selecting an appropriate height below which are included all nodes that need to be processed. It is good practice to calculate scale data for all clusters of the dendrogram. In this specific example, the full dendrogram is displayed below a word height of 30. We can thus select the value in the Blend command line. The command for the execution of Blend in synthesis mode includes the -s string, followed by the word level selected, 30 in this case. It is also possible and useful to use ALCV and LCV values rather than the word height. In the synthesis mode, pointless and aimless are executed once for each cluster. The resulting files and all relevant logs are stored in a new directory called merged files. Up to this point, we have not made use of keywords and have accepted default values. This time, before running blend in synthesis mode, we create a keyword file, and for example, we can call it bkeys.dat, although you can call it whatever you want, whatever way you want. And this file has the content here illustrated. Essentially here, we are limiting resolution to 1.9 angstroms to all clusters. We are also asking pointless not to stop if the difference in cell parameters is considered too large. This is described by the pointless keyword tolerance. A large value, like 100, means that very large differences in unit cells are tolerated. Blend is eventually executed in synthesis mode by feeding the keyword file with a Unix symbol for input redirection, as you can see here. This time the program doesn't halt and execute to the end. And you have here the keywords used reported in the log. Now, scaling and merging statistics are updated at each node being processed so that scaling can be monitored. Some space groups, the polar groups more specifically, can have indexing ambiguities. This means that the same reflection can be indexed differently in two different datasets. To maintain consistency among datasets, a reference dataset needs to be selected. And this dataset is used by Pointless to explore alternative indexing. Users can select an external dataset not belonging to the group of data under investigation via the keyword data ref. Eventually, overall statistics for all clusters are collected in a single table. The same table is included in the merged file directory with the name mergingstatistics.info. And with this one, you can have an overall view of all the statistics for all the clusters in the dendrogram. Now, quite often, the synthesis mode returns what is needed to carry on with phasing, model building, and refinement. Sometimes, though, especially while working with difficult structures and especially non-isomorphous data, it is necessary to carry out some further selection and filtering of datasets in order to create combinations not included in the clusters. In Blend, there is a possibility to annotate dendrograms with merging statistics computed in synthesis mode, so to make the selection and filtering process easier to perform. This can be achieved by running Blend in graphics mode using syntax -g, where the capital letter after the -g string denotes the type of graphics to be produced. At present, there are only two types available, both annotated dendrograms. More types will follow soon. As the original dendrogram can be very dense with objects and branches, the annotated dendrogram can focus around specific nodes. The first number of this command line indicates the selected cluster node, while the second line indicates how many merging levels downward, including the one containing the selected node, should be included in the annotated dendrogram. In this example, we would like to display the whole dendrogram, and thus we focus on the top cluster, cluster 25, and choose to go down of enough levels, 12, to reach its bottom. In the displayed annotated dendrogram, 3 numbers are written around each node. The blue number is the overall RMES, the green number is the overall completeness, and the red number is the resolution as estimated with the CCA half greater than 0.3 criterion in Aimless. The examination of the annotated dendrogram brings immediately to light the possibility of improving statistics for all the nodes indicated by the green arrows. The way to achieve this is by running Blend in combination mode using the string -c. Here we use a special syntax where clusters are included in square brackets, while datasets to be discarded are included in double square brackets. For example, cluster 15 is definitely made worse by dataset 23, and accordingly, cluster 21 is also made worse by dataset 23. But there could be other datasets that deteriorate statistics for cluster 21. We can quickly explore which one by running the two lines with 21 within square brackets and 23 and 16 or 23 and 22 within double square brackets. By proceeding tentatively in this way and examining at each steps the statistics displayed, we are able to filter out unwanted datasets from specific cluster, thus achieving improved statistics. Here, blend has been executed 5 times in combination mode. You can easily appreciate that the R-miss for cluster 23 dropped from 0.388 to 0.163 once datasets 22 and 23 were eliminated. Results from all runs in combination mode are progressively stored in directory combined files, together with the merging statistics.info file to rapidly check all overall statistics. To conclude this tutorial, I would like to describe the filtering variant of the combination mode, string -C, which has been recently added to Blend. When this variant is used, the program attempts at eliminating, one at a time, all datasets composing the specified cluster or group, until some user-selected completeness is reached. The related keyword is completeness, which has a default value of 95%. But here we choose, for the tutorial, a value equal to 99.8%, just to compare the result with what we have obtained earlier, discarding dataset 22 and 23 from cluster 23. A maximum number of cycles is allowed and implemented via keyword maxCycle, which has a default value of 5. At each cycle, the dataset to be discarded is the one having highest overall R merge. This screenshot shows how cycling occurs with the F variant of the combination mode. It is interesting to see that datasets 22 and 23 have been the first to be discarded, confirming the choice we had made earlier to improve statistics using the symbol combination mode. But cycling carries on here because the completeness stays at 99.8% even when dataset 15 is eliminated. Eventually, completeness drops at 98.9% after elimination of dataset 16, and this causes cycling to stop. The output is given in any case by the cycle which has reached the lowest RPIM, cycle 3 in this case. Now, the RPIM is preferred over the R-miss because the RPIM takes into account both data precision and data multiplicity. Like any other result produced in combination mode, results from the F variant of the combination mode are stored in the combined files directory, and the related statistics listed with all statistical runs in combination mode. Now, another variant is also available for the combination mode, and this is called the pruning variant, syntax -C. This is an automated procedure to remove images from individual dataset. And it has been thought as an improvement on data affected by radiation damage in all those cases where the procedure carried out in the analysis mode is not successful enough. Due to time constraints, I cannot provide details for this variant here, but plenty of explanation is available in the documentations. As promised at the beginning of my webinar, I'd like to list a couple of web links where you can find the tutorial discussed today and other tutorials on Blend. One link refers to the official CCP4 webpage, and the other to material in my personal webpage. In the above sites, you can also find the official documentation, as well as the downloadable data for the tutorials, like the 28 sweeps of lysozyme used in this webinar, so that you can try the tutorial by yourself. You are also welcome to contact me directly via email and I normally manage to reply very soon to anyone's email. To finish, I have written most of the blend code, but main ideas and lots of help has also come from the following scientists. Gwyndaf Evans is Blend's principal investigator. He is also principal beamline scientist of the VMX-M beamline, currently under construction at Diamond, and group leader of the East branch of DIAS, the novel software for X-ray data integration. David Waterman is responsible for the Blend GUI within CCP4I. He is also one of the DIAS developers and is a member of the CCP4 core team. Pierre Allaire is my main collaborator in the research connected to the development of Blend. He has also helped me with the tutorials and is an established support scientist at the Diamond Synchrotron. And I also owe special thanks to Phil Evans, the author of Pointless and Aimless, for having provided essential C++ code for the program. And to conclude, special thanks go to the CCP4 core team for their endless efforts to distribute and maintain Blend and other very useful programs for macromolecular crystallography. I would like to also thank you all for the attention, and I'm available to take any questions.
Thank you very much, James. If anyone has questions, they can chat those to me. I could also unmute a mic if you are mic'd at your location. So you can chat those to me and I'll pass them on. What features are you adding to Blend now? What do you think you'll be adding in for newer releases of Blend?
So the one I'm working on now is on this representation of reciprocal space completeness. Obviously, when you have redundancy of data sets and you have to perform a selection and having equally valid data sets, first thing you would like to achieve is a completeness, and it's interesting to quickly spot which data set is making the regional reciprocal space completeness more complete, of course. And with a diagram, which covers, where you can see easily which data set cover which region of the reciprocal space, that should be easy to do. I'm also trying to come with better way to spot this decay due to radiation damage at the beginning. I mean, the procedure we have right now is with the unscaled data. So it's very little processing being done on these data sets at the beginning, basically only the averaging of intensities in reciprocal space.
Yeah, so on a sort of related note, are there any accounting for mosaicity and or plans to account for mosaicity? Like, could you sort of exclude frames or data sets based on an increase in mosaicity or a change in mosaicity?
Well, certainly this is a good suggestion, which I can take into account. I didn't have any plan. I have to say that at the very beginning of when Blend was still not a program of our investigations, mosaicity used to be one of the descriptors for doing the cluster analysis. We had to discard it because basically what we wanted was to achieve completeness and redundancy, even with data sets which had different mosaicity, because ultimately they were isomorphous in terms of the structure they were describing. But in fact, in the long term, it should be possible once a graphical interface, a very complete graphical interface would be available for Blend, to actually exclude or select data sets based on a number of descriptors, and one of them should include mosaicities. Then there should be also in descriptors to include the anisotropy completeness, anomalous signal, and this sort of thing. So basically, working with multiple crystals is not done just in a unique way. At the moment, Blend is optimized to achieve completeness and redundancy. But very soon, we would like to add other features. There will be people that want to have strong anomalous signals, so to do good subphasing. But there are other people that want to have a proper isomorphisms, therefore want the crystal to be tight. So depending on what you want to do, you should really try to select certain type of descriptors. Another possibility is to connect blend to some slices of a map in relation, for example, to ligands, because there will be ligands connected to the structure for certain crystals and less connected with other crystals. And perhaps the user would like to spot all those crystals which allow a better detection of the specific ligand.
Yeah, that would be fantastic if you could sort of optimize on occupancy of a certain binding site or something based on.
Exactly, for example, yes.
All right, I think with that, any other questions? I think with that, we'll wrap up. Thank you very much, James. And
Thank you.
We'll end here, and I'll follow up with you offline by email.
Okay, thank you very much.